Hello everyone. The title of this video is Finding and Evaluating Inverse Functions. So every example I'm going to be doing in this video is taken directly from a free online textbook at openstax.org. I'm in their Algebra and Trigonometry text, section 3.7, Inverse Functions, and I'm under the heading Finding and Evaluating Inverse Functions. Alright, and each example I'm doing is either going to be an example from the reading or one of the try it problems from the reading or one of the exercises at the end of the section related to this particular objective. Alright, so I have my first examples written out here. Alright, so first example I want to do for you is the try it number 5 from the text. So let's take a look at that. So I can read through and look at examples, and here's try it number 5, and we're asked to say using this table given to us here, a table representing a function that looks like it takes minutes to miles, right? Input t, output f of t. Find and interpret, part A, what's f of 60, and part B, what would be f inverse, right? The little -1 symbol there means inverse, right? F inverse of 60. All right, so I'm going to write this table out and come back and talk about these things. Okay, so I've written out the table they've given us. Or again, the top row is the inputs of function f, the times in minutes it looks like. And f of t, the second row, are the outputs in miles of this function called f. So we're saying that f of t equals mileage. I'll say m for miles, right? This is mileage. Now, this is what they call a one-to-one function, right? It's a function since every input goes to exactly one output, and it's one-to-one since every output is only appearing once as well, right? 20, the output of 20 doesn't show up anywhere else, right? The only thing that maps to 20 is 30, and the output of 40 is only appearing once, right? So this is a one-to-one function, and if you've seen in previous videos of mine on inverses, only one-to-one functions have inverses that are also functions. And another thing hopefully you recall from previous videos on inverses that I put up, an inverse is simply a reverse mapping. Just a reverse mapping. So if f of t equals m, right, if my input is time and output is mileage in this function f, then f inverse takes mileages to times. So if f takes an input of time to an output of mileage, then f inverse will reverse that. It'll take an input of mileage and output a time. So in part A, they asked us, what is f of 60? So because this is f, right, that means the input is a time in minutes. And so the output needs to be a mileage. Right. So I look at my table here, input 60, and then f of 60 is 50. Input 60, output 50. Okay. Now what does this mean? This means that, maybe we traveled 50 miles in 60 minutes, right? 50 miles is traveled in 60 minutes. Right. Now part B, maybe I'll put this in a little box. This is what they wanted from part A, right? It's 50. Now part B asks for what is f inverse of 60. Now, being that this is f inverse, right, it reverses the original mapping. So instead of the input being time and the output being mileage, this is an input of miles, and the output needs to be a time in minutes. So basically, just again, look at it in the other way, reverse the mapping. So f inverse of 20 would be 30. F inverse of 40 would be 50. We're asked for f inverse of 60, so we're here in this column. When the mileage is 60, what's the output? It's 70. And interpret this. This means, according to this, we'll have traveled 70 miles. I'm sorry, it would take 70 minutes to travel 60 miles. Right, it takes 70 minutes, right, because the output's in minutes, to go, 60 miles, right? The input's in miles this time. Right, but it's very simple. Just a reverse the mapping, reverse the arrow if you want to draw an arrow diagram. Okay. But yeah, so if you think of inverses as reverse mappings, just going, switching inputs and outputs, it'll make things that much simpler. Great. All right, so now the next example I want to do is example 6 from the reading. So let's go back to the text. Scroll down a bit more reading for you to do. Here's example 6. And this is evaluating a function and its inverse from a graph at specific points. All right, so here we're given a graph of a function g, and we're asked to state what's g of 3. And this is a graph of a one-to-one function, so its inverse would also be a function, and I'll actually draw this. All right, and then what would be g inverse of 3? Right. So again, I'm going to draw a rough sketch of this graph they're giving us of this function g, and we'll make another rough sketch of a function of what g inverse would look like, and answer their questions. Alright, so again, a very rough sketch of the graph of g they gave us. I put it in pink here. So I can, with this graph of g, I can answer their questions. I mean, they said, what's g of 3? Alright, so x value 3, what's the y value? Alright, so x value 3, the output is 1. Alright, so that's one answer. G of 3 is 1. Then the other question they asked, I could answer with this graph here. They said, well, okay, this is a one-to-one function. It passes the horizontal line test, so its inverse is also a function. What would be the value of g inverse, right? G with the little -1 above it, at 3? All right, so g inverse of 3 equals what? I'll put a little question mark here. Well, another way to ask this is, g inverse of 3 equals what? G of what equals 3. All right, these kind of mean the same thing. Right. So, because again, this is just reversing the mapping. So in G, what number gives me an output of 3? All right, because that output of 3 will become the input in G inverse. So G of, if you look at the output of 3 here, G of 5 is 3. So that means that G inverse of 3 is 5. Now again, if you don't see it right away from this original graph, you can make a graph of G inverse. Not a problem. All right, G has 3, 1. Remember, in inverses, you just switch the mapping, reverse it, switch the x's and y's. So if the graph of G has 3, 1, the graph of G inverse will have 1, 3. And the graph of G has 5, 3. So the graph of G inverse will have 3, 5. Right, and there's the answer to that, that second question that I had there. G inverse of 3 is 5. And instead of having the x-axis as a asymptote, this graph will have the y-axis as an asymptote. And I'll show you, it should look something like this. And there's G inverse. And another thing I pointed out, I did point this out in a previous video as well. If you look at the graph y equals x, remember that line with a slope of 1 going through the origin, right, there's y equals x. Remember, the graphs of inverses are just a reflection across the line y equals x. If you were to flip these, if you were to fold the line y equals x, these two graphs would meet each other. Right? So, and again, it's a hand drawing. It's not the best, but hopefully you can see kind of how these would be reflections across the line y equals x. But yeah, so g of 3 is 1, so input 3, output 1 on g. G inverse of 3 is 5, right? Input 3, output 5 on g inverse, because again, I saw that 5, 3 was on g, so 3, 5, right? Just reversing the mapping would be on g inverse. I hope that's clear. And that is all that we are asked to do in this example 6. All right. My next example, example 3, I want to do try it problem number 8 from the reading. All right, so back here, again, you got some other stuff for you to do. Try it number 6, example 7, try it 7, example 8, all this stuff. Example 9. I just want to look at try it number 8. Alright, so what is the inverse of the following function? F of x equals 2 minus the square root of x. So we're going to write an equation for f inverse, and I'll talk about how to do that. State the domains of both the function and the inverse function. And I'll do this. I'll take this one step further. I'll also state the ranges. Alright, so we're given the function f of x equals 2 minus the square root of x. Right. Now if you want, I'll go to the Desmos.com website, free online graphing calculator. But I'm going to graph this right now, right? The domain is, just all the numbers greater than or equal to 0. Because you got this square root of x here, right? You can't plug in a value of x that's negative, because the square root of a negative number is imaginary, and you can't plot that on the real number coordinate axes. And this would just be the graph of the square root of x reflected across the x-axis and moved up 2. So you'd have 0, 2 as a point, 1, 1 is a point, 4, 4, 0 would be another point, and it's just like the square root graph, but reflected and moved up 2. So here's the graph of f. Very, very rough graph, right? Like this. Kind of like half a parabola opening to the right here. There's the graph of f. And I could, based on this picture, I could graph f inverse right now. Here's 0, 2 on f, so 2, 0 would be on f inverse. 1, 1 would be on both of them, right? You just switch 1 and 1, it's still 1 and 1 again. And then instead of 4, 0, you'd have 0, 4. And it would be like this curve, just reflected across the line y equals x. So this graph here. And again, like a half a parabola, just half a parabola. There's f inverse. Right, there's f inverse. Alright, now how do I find an equation for this? I have to find an equation for this. One thing else I'm going to point out is I know the range of this function f as well. I'll point that out. See, a graph of f is all values 2 and lower. Right, so from negative infinity up to 2, including 2. If you go up the y-axis, the graph of f has a range of negative infinity to 2. So keep that in mind. And these are going to be the domain and range of the inverse, just switched. Remember, the domain of a function is the range of the inverse, and the range of a function is the domain of the inverse. Alright, so finding inverses, finding equations for inverses. So in the original equation, where y is the same as f of x, right, where y equals f of x, you switch all y's with x's and x's with y's. That's what happens in an inverse. Alright, so this equation here I'm going to write like this: y equals 2 minus the square root of x. It's the same thing, right? Y represents f of x. And now I will do the inverse, right? We're going to invert this, and it becomes the following equation. Instead of y equals 2 minus the square root of x, y's become x's. X equals 2 minus the square root of y. And now we just solve for y. And here, right here, y represents f inverse of x. Right, we inverted. So y doesn't represent f of x like in the original, it represents f inverse of x. And then we solve for y, and then that'll be the rule. So it's simply just, I would add the square root of y, subtract 2, multiply by negative 1. So we get the square root of y equals, 2 minus x, right, or negative x plus 2, just adding, subtracting x. Then square both sides. Y equals, the quantity 2 minus x squared, which is really the same as x minus 2 squared if you want, the quantity x minus 2 squared. Now the graph of this, right, now this is f inverse. F inverse of x is, I'll just use the x minus 2 squared. This is the equation for our inverse, but you got to be careful. Right? We got to make sure the domain and range match up, right? Because look at this, my pink graph here. The graph of the inverse here is not, this function here, if you were to look at the entire graph, would be a whole parabola. But we don't have the whole parabola. We only have the part of it with this domain and range switched up, right? The domain of this function is not all real numbers. All right, I know you would think it is because it's just x minus 2 squared, right? You're not going to divide by 0, there's no square roots. The domain is not all real numbers. The domain of a function and its inverse, right? The domain of one function is the range of the inverse. And the range of the original function, right, from negative infinity up to 2 is the domain of the inverse. So it's just from negative infinity to 2. And you can see that in my pink graph. All right, the domain of the pink graph is from negative infinity on the x-axis up to 2. All right, so the range of the original is the domain of the new function, of the inverse. And the range of the inverse is just the domain of the original, right? Everything from 0 and up. And you can see that in my pink graph. Right? The range of the pink graph, the y-coordinates are from 0 upward, 0 to infinity. Right, so that's why I wrote the range as well, because it is very helpful if you know the range, right, and the relationship between the domain and range of inverse functions. Right, the domain of one is the range of the other, and vice versa. Right, the range of one is the domain of the other, if they are truly inverses. All right, and again, let me Let me show you this, a better picture on that Desmos site. Go to desmos.com. It's a free online graphing calculator. All right, and I'm going to put in the function they gave us, f of x equals, 2 minus the square root of x. And I'll put in, y equals f inverse of x. What's wrong there? F is a function, try using parentheses. Oh, are they gonna... I see. Do I have to do that for inverse? Okay, so guess you can't do that. That's unfortunate. Well, then our other thing was y equals, x minus 2 squared, but again, not the whole thing. Right? Not the whole thing. You see the blue graph and the black graph? The black graph is not a reflection across the line y equals x. And in fact, let me put up the line y equals x here, and I'll make it a dotted line, a dashed line. You see, the blue graph, if you reflect it across the red line, would be just the left half of the parabola. Right? You see, you got here's 0, 2, so you should just have 2, 0. And there's 1, 1 on that. There's now whatever this point is should be over here. But the right half of the parabola shouldn't be there. So I'm gonna get rid of it by after y equals x minus 2 squared, put some braces. Say, well, x needs to be less than or equal to 2 only. All right. And there you go. All right, there's a good looking graph of a function and its inverse. All right, and that's the graph I drew by hand. Okay. But yeah, so graphs of inverses are reflections across y equals x. X's and y's switch, they're reverse mappings, however you want to say that, right? But in the equation, right, you take the original, you switch y's with x's, x's with y's, solve for the new y. Okay, so now let's go back here, and that's it for that try it problem number 8. All right, so now for the next examples. These are taken from the exercises, if you want to take a look at those from the book. I have 2 instructions. One, find the inverse function, right? So that's where I do the switch y's with x's, x's with y's, and solve for the new y. Then state the domain and range of the function and its inverse. All right, so for this first one, I'll do a drawing by hand. It's a pretty easy one. Now it's just y equals x plus 5. And this is just a line, right? It's got the point 0, 5 on it. It would have the point, negative 5, 0. Right, and 1, 6 and all that, and here it is. Right, there's f, just a linear function. There's f, and the domain and range is all real numbers. I'm hoping that's obvious. All right, so the domain is all real numbers. The range is all real numbers. It's also a one-to-one function, right? It passes the horizontal line test. So that means the inverse will also be a function, which is great. So now let's actually invert. So take the original equation here, y equals x plus 5, and I switch y with x and any x's with y's. So I get this equation, x equals y plus 5, and then we solve for y. Y equals x minus 5. And this y, the original y represented f. This y represents f inverse, right? So this is f inverse of x equals x minus 5, right? So that's part 1. Right. And let me graph this, right? So this would have 5, the original had 0, 5, so this will have 5, 0. And it does, right? If x were 5, the output would be 0. This had negative 5, 0. This would have 0, negative 5. And you can see that, right? When x is 0, the output would be negative 5. And there we go. And it's another line with a slope. It should be parallel to the other one. They both have a slope of 1, but there's f inverse. And again, you can see this is a reflection across the line y equals x, right? Y equals x is another line with a slope of 1. Here's y equals x. And hopefully you can see the reflection. And the domain and range is very simple again, right? The domain of this function is the range of the original, right, which is all real numbers. And the range of this function, right, is the domain of the original, again, all real numbers. And you can see that in my picture as well. Right. So, pretty easy, that one. Alright, so I'm not even going to go to Desmos on that one. Right, I think it's pretty easy to see with this hand drawing. Okay, and let's move on to the next example. It's very similar. Got another linear function. So here we have f of x equals 3 minus x. Alright, so again, this will be one I'll just do by hand. And the examples after this, I'll go into Desmos and draw better pictures there. So, again, you could also call it y equals 3 minus x, right, where y is f of x here. This should have the point 3, 0 on it, and 0, negative 3, or sorry, 0, 3, 3 minus 0. Right, 0, 3, 3, 0, and here's the graph of f, right, just this line here with a slope of negative 1 and a y-intercept of 3. Right, there's f. And what we're going to notice is that when you reflect this across the line y equals x, right, here's y equals x, which would be perpendicular already to this line, right, because they have a slope, they have slopes that multiply to be negative 1. It's just going to be the same graph again. Right, if I reflect the pink graph across the line y equals x, it's the same graph, and watch, we'll get the same exact rule for the inverse. So I'm going to invert here, meaning change y's to x's and x's to y's, so x equals 3 minus y, and then I solve for the new y. Well, it'd just be y equals 3 minus x. And this y, remember after inverting, this y represents f inverse. Right, and it's the exact same function. So, if I were to draw that again, it would be right on top. They're the same exact thing. So this function is its own inverse. Right, and it's actually, basically any line that's perpendicular to y equals x will be its own inverse. And those are the only things really that'll be its own inverse that you're going to see for a while. There are other functions, of course, that are their own inverse, but these are the pretty basic ones. And the domain and range for both of these is all real numbers again, as you can see. Alright, domain's all real numbers, range is all real numbers for both functions. Right, so I'm just going to draw an arrow to both of them. It's the domain and range for both of them. And great. Again, a pretty easy one, especially the linear functions, graphs of lines. Alright, the next one, a little trickier. You have a rational function. Now this one I'm going to go to the Desmos site and show you a better picture. Okay, so function here, the domain, I can tell you right now, is every number except negative 4/5, right? So that's from negative infinity up to negative 4/5, right? Not including negative 4/5, and then union, and then from negative 4/5 to positive infinity. Right? And that's all I can really tell you right now without trying to make a graph. I don't know the range exactly, right? But we can use the inverse to help us find the range. Remember, the domain of the inverse will be the range of the original. Alright, so this is y equals 2x plus 3 divided by 5x plus 4. And now let's invert. Alright, so y becomes x, and the x's become y. So x equals 2y plus 3 divided by 5y plus 4. And we solve this for y. Alright, so one thing to do here would be multiply both sides by 5y plus 4. So x times 5y plus 4 would be 5xy plus 4x, right, distributing the x, equals 2y plus 3. Then I get all the y terms to one side. So we have 5xy and then minus 2y equals, and then all the non-y terms to the other, 3 minus 4x, or negative 4x plus 3, whatever you want to write. And then both these terms on the left here have y in it, so I can factor that out. We have y times the quantity 5x minus 2 equals 3 minus 4x, and then I can solve for y very easily by dividing by 5x minus 2. So y equals 3 minus 4x divided by 5x minus 2, and there's, this y represents f inverse, right? F inverse of x is 3 minus 4x divided by 5x minus 2. Alright, so that was part one, right? Find the inverse, and then state the domain and range of each, which, again, I should be able to do now. We know the domain of the original is every number except negative 4/5, right? Because that'll make you divide by 0. And this function here, the domain of f inverse, is all the numbers except 2/5, right? The denominator is 5x minus 2. If x were 2/5, that would make that 0. So every number except 2/5, negative infinity up to 2/5 in union with, and then 2/5 to infinity. And now I know the ranges for each of these. Right? Since I have the domain for each of them, I now know the ranges. Remember, the domain of one function is the range of its inverse. So the range of f inverse is going to be everything but negative 4/5, right? Just like the domain of the original. So from negative infinity to negative 4/5 in union with negative 4/5 to infinity. And then, since the domain of f inverse is everything but 2/5, that's the range of f. Right? The range of f is every number, every real number except 2/5. Right? So from negative infinity to 2/5, and from 2/5 to infinity. Okay. So yeah, that's the relationship between the domains and ranges of inverses. The domain of one is the range of the other. And you just got to remember that domain means x coordinates and range means y coordinates. So now let's look at the graphs of these. Alright, so back on the Desmos site, let's see, the function we were given was, y equals, and you had 2x plus 3 in the numerator, 5x plus 4 in the denominator. And let me clear out this stuff, this other graph here. Alright, and I'll keep y equals x up there so we can see the reflection. But look at this, right? All the points on the blue graph have x coordinates that are everything but negative 4/5, and the y coordinates are everything but 2/5, right? If I put in y equals 2/5, you'll see it's going to run right in between them, right? Right in between them. That's not being touched. Right. Sorry, it came up as the same color, but yeah, so the domain is every real number, all x values except negative 4/5, and the range is all y values except 2/5, like we stated on the paper. And then we switched x and y's, solve for y. We got y equals, right, our f inverse was, 3 minus 4x in the numerator. and 5x minus 2 in the denominator. And look at these two graphs, the blue graph and the green graph. Hopefully you can see it, but they are definitely a reflection across the line y equals x. All right, hopefully you see it. Like, you see how the green graph has 3/4, 0. The blue graph should have 0, 3/4. And look at that, 0.75 there. You know, the blue graph has -1.5, 0. The green graph should have 0, -1.5, which it does. See, these are inverses. They are a reflection across y equals x. The x's and y's got switched. Right. So our equation looks like it's good. And look, the domain is all x's except positive 2/5, and all the y and the range is all y values except -4/5. Right? It's just the domain and range of the original graph switched. Very nice. All right, so let's do that again with I feel a much simpler graph. And just a basic square root function. Alright, so the domain of this function, remember you can't take square roots of negative numbers. That'll be imaginary, and you can't plot imaginary numbers on your xy coordinate plane, Cartesian plane. So it's just numbers from 0 to infinity, including 0. So I got a bracket on 0. So, you know, square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. And here's the graph of f. Right, f of x equals the square root of x. Alright, now I'm going to put in the line y equals x. Here's y equals x. And let's reflect this across the line y equals x. Now 0, 0, and 1, 1 will still be on it, but instead of 4, 2, you'll have 2, 4. And what we're getting here is half a parabola again, but this time opening up. Alright, there's f inverse. Now we just need an equation. We need a rule for f inverse. Now I can already tell you the domain and range, right? For f, the domain is all the numbers 0 or greater, and the range is also 0 and greater, right? You know, y equals 0 and up, right? And so this is going to be the domain and range of the inverse as well. Right? So we'll have f inverse of x equals something with the same domain and range. As you can see from my green graph here, the domain is 0 and up, the range is 0 and up as well. Right? Now I just need a formula for this part of the graph, this green graph. So again, the original I can think of as y equals the square root of x. Then we invert, right? Switch y's with x's and x's with y's. And then very simply solve both sides by squaring. Y would equal x squared. Right? So f inverse is x squared, but not the entire x squared, right? It's only the x squared with the domain of the non-negative numbers. Right? It's not the entire y equals x squared, it's just the right half. Just the part where the domain is from 0 to infinity. Okay? Wonderful. Alright. Alright, and then my final examples are a little, we're still doing inverses. Actually, I've got a couple pages left. So my next examples, though, are even simpler, I feel. They're from other exercises in the end of the section. So our instructions are to evaluate or solve, and we're supposed to assume that our function f is 1 to 1, right? I mentioned earlier, a function needs to be 1 to 1 in order for the inverse to also be a function. All right, so that's why they're telling us that. So really all we're doing here is evaluating or solving whatever they're asking us for. So number 8, if f of 3 is 2, what would be f inverse of 2? Well, that'd be 3. It just goes right back. right, just reverses the mapping. If f of 3 is 2, right, so I mean you could do I mean this is kind of silly what I'm doing, but you can do this if you wish. Here's the xy plane. You know, if f of 3 is 2, right, so input 3, output 2, so there's f. The graph of f has the point 3, 2. The graph of f inverse would have 2, 3, wouldn't it? Right, this point would be on the graph of f inverse. So if f of 3 is 2, then f inverse of 2 would be 3. Right, so there's the solution there, 3. Very, very simple stuff. And then very similarly here, if f inverse of negative 2 is negative 1, then what would be f of negative 1? Well, it would just take you right back to negative 2. It's very, very easy. And once again, if you want to draw a little picture, you can, and it can't hurt. So the point, you know, negative 2, negative 1, that point is on the graph of f inverse. Well, if that's on the graph of f inverse, then, you know, negative 1, negative 2 would be on the graph of f, right? And that's what this is saying. Right? And those are reflected across the line y equals x, right? Every point on a graph and its inverse are just reflections across the line y equals x. Very, very easy, in my opinion. And then here's my last page. Alright, so example 10, I want to do exercise 38 from the text. So let's take a look what that looks like. Alright, so going back to the text, scrolling down until we get to exercise 37. No, 38, I'm sorry, 38. Alright, so we're using a table, kind of like earlier in the video. It says for the following exercises, use the values in table 6. So we have a function f represented by this table. X values in the numerator in the first row, and then f of x, the outputs, in the second row. And then if you just switch these, you'd have the inverse, right? Instead of 0 going to 8, you have 8 going to 0. That's f inverse, right? So for number 38, we're asked to solve f of x equals 3. Right? F of x equals 3. So basically, what input, right? What input gives you an output of 3 in this function f? And that's simple, right? I go to my table. I look, where is f of x equal to 3? That's here, right, where my cursor is. Sorry, you can see it now, the arrow floating around. Where is f of x equal to 3? That's here in this column, and that's when x equals 7. Right, so the solution to this equation, it looks like that's the only time f of x equals 3. The solution to this equation is x equals 7. And that's it, right? That's all they want, right? F of 7 is equal to 3. That satisfies the equation. So the solution is x equals 7. Very, very simple. Again, in my opinion. All right, and then my final example is exercise 40 from using that same table. Exercise 40 is solve f inverse of x equals 7. So I know, again, they don't have a table for f inverse. They have a table for f. They have a table for f. But all you need to do is reverse it, and you'll have a table for f inverse. Very, very easy. All right, so back on the paper, I'll write out that equation. We're asked to solve f inverse of x equals 7. But remember, if f inverse of blah equals 7, that means that f of 7 must be blah, right? If f inverse of x is 7, then f of 7 must be x. So these are the same equation. So it's the same thing as, in this table for f, when the input is 7, what's the output? Right. So going back to the table for f, when the input is 7, I'm here, the output is 3. So the solution to the equation is x equals 3. Right? F inverse of 3 would be 7. Right? That's a true statement. And again, go back to the table and just reverse it. Here's the table for f. If you did f inverse, you'd have when x is 8, f inverse is 0. When x is 0, f inverse is 1. When x is 7, f inverse is 2. Right? When x is 3, f inverse is 7. And that's what was asked for. Right? When is f inverse equal to 7? When x is 3. Okay, so again, if you got that concept down, that inverses are just reversing the mapping. You switch x's and y's, the domain and range switch, the graphs get reflected across the line y equals x, x's and y's switch. However you want to think about that. If you got those concepts down, all these exercises, all these problems from this section should be relatively simple. Great. And I'm hoping that watching me go through these 11 examples here in this video help you in some way when you're asked to evaluate or solve, find and evaluate inverse functions on your own. Right? And thank you very much for watching.